say geology is something I always want to know more about, and I don't know very much. So I'm really looking forward to your program tonight. Please welcome Lon Abbot.
So, thanks everyone for coming. Hopefully it'll be worth your while. Can everybody hear me okay? All right, well, so you may see the title, The Geology of Estes Park Rock Climbing, and that isn't necessarily what you signed up to come see. So when Celeste asked me to give this talk, she guided me in terms of what might be of interest to this group, and it was sort of the general geologic history of the Estes Park area, as well as sort of how the landscape is sort of sculpted by geomorphic processes. So I gave this talk several years ago up in Estes Park, and despite the title with it being rock climbing, I think that actually this is going to deliver what she asked me to do. So the rock climbing part, we're going to go through to just a couple of slides here at the beginning, and then we'll get into to what hopefully you've come for. All right? So, let's see. Why is it not advancing? Oh, I guess I have to advance it here on this Zoom. So, Rocky Mountain National Park, as many of you know, is a climbing mecca. And so what is its climbing like and why? And these are photos of the climbing in the area. Rock climbing and geology are intimately related. I actually taught at a small liberal arts school in Arizona for 10 years, and I taught a rock climbing and geology class where we would actually go out and climb and then discuss why the climbing had the characteristics that it does. And really, the type of rock you have dictates the climbing style. And as well as what kind of weathering regime you've got. And there are two main styles of climbing. There's face climbing and crack climbing. And Estes Park has both kinds, but it's most renowned for its crack climbing. And so I want to try and explore why that is, and that really leads into the aspects that you're interested in. So part of it is, and I don't know why this turn up the volume is there. It's not on my screen here, so I can't turn it off. It's not a big deal, but yeah, I would have closed it out if I'd had it, but it's not showing up on my computer. Well, part of that is because the climbing here is on granite. So there are two main types of rocks here in the Estes area. And granite is one of them. The other one is gneiss, which I'll show you a picture of in a little bit. But so lots and lots of granite around here. And cracks are really common in granite. And then the other aspect, which is the other piece that I was asked to talk about, is that granite has been sculpted by glaciers and what we call paraglacial processes. So paraglacial processes are where you don't actually have a glacier itself, but it's quite cold, and so you'll get freezing and thawing, freezing and thawing. That is really quite important. You've got that today, and you had even bigger areas that were affected by paraglacial processes about 20,000 years ago when there were glaciers that came all the way down to Estes Park from the Continental Divide. Okay, so let's turn our attention to granite. Granite is an igneous rock. There are these three types of rocks: sedimentary, igneous, and metamorphic. And it's an igneous rock, which just means that it formed from a magma body. It was hot enough to actually melt the rock, and it came out. It was magma, which is what we call it underneath the surface. And then if it erupts on the surface, we call that lava. And so there's a close-up of some granite. But the granite that you see around here, even though it's igneous, it wasn't formed by a river of lava like you've got here. That is a type of igneous rock that is called extrusive, and that's the stuff that gets erupted at the surface, okay? But granite is a magma that stalled out and formed a magma chamber underground, in fact, miles underground, and it never erupted, so it cooled very, very slowly and steadily. And that is why you've got this texture that you can just visibly see individual mineral crystals here that are different colors. You've got white ones, you've got pink ones, clear ones, and black ones. And those are 3 or 4 really common minerals that form the 2 most common elements in the Earth's crust are silicon and oxygen. And those chemically bond together really easily and make what are called silicate minerals. And then you've got a fair smattering of things like calcium and iron and magnesium and sodium and potassium, and those will glom on to the silicates to make these different kinds of minerals. And when you cool a magma, when this is all molten, and you cool it down, you will crystallize out different minerals, and so those elements will attach onto these different minerals to make to form these different minerals here of these different colors. And so granite is an agglomeration of that. But because you've had time to slowly cool, the crystals are big enough to see with your naked eye. Okay, so how and when did the Rocky Mountain National Park granite form? Let's actually start with, and then how did it acquire all those wonderful cracks to climb? So we're going to start with a little discussion about this second part, and then we're going to launch into the history of Estes Park, geologically speaking, by tackling the granite. Okay, so I've told you already that if it's a granite, that magma cooled slowly deep underground, miles underground. So that means that if we see granite on the surface, you already know that you had to have removed literally miles of rock that used to sit on top of that. So that's what I would consider a pretty extraordinary thing right out of the gate is, wow, how and when did you remove all that material, miles of material that used to sit above this to expose this granite? And we'll get to that as we tell the story. So Lumpy Ridge, when the Lumpy Ridge granite was a magma, what is now Estes Park was miles below the surface. Okay, as that material is removed, the pressure on the granite decreases. So an analogy would be, if I lay down on the floor and everybody piles on top of me, I've got a lot of pressure on me. And as one after another of you gets off, the pressure gets less and less and less, and that pressure has squeezed me, and so as the pressure gets less, I'm going to sort of expand up a little bit. But because we've got a lot of water in us, we can expand in a sort of elastic way, but rocks are brittle, and so as that pressure gets released, they actually expand like you see here. All these black lines are cracks. The cracks are accommodating that expansion. And so you can see all over the Estes area, you've got all these cracks that are sort of arcuate like this, and this is called exfoliation. It's not that different from if you exfoliate yourself with a sponge or something, but you can see these cracks here, and in the diagram looks almost like an onion that's peeling, and that's what exfoliation is. And you've got some really great examples of these exfoliation domes here. Okay, now let's turn our attention to the granite itself, and so we're going to take a journey through time, going back in a time machine, if you will, to the Estes Valley at different times in Earth's history, and see what was going on then. And it turns out that the granite is one of the oldest events in that. But I'll try and bring us up to the present, and then we'll finish with a little bit of what's been happening recently with that periglacial freeze-thaw cycle that's finished up the cracks. So we've got to take a journey through geologic time, and our story begins the Earth. Well, you can't see it because of that, but this is 1,750 million years ago, or 1.75 billion years ago. So the Earth formed about 4.6 billion years ago. And for almost, for 2/3 of that time, what we know of as Colorado didn't exist. These are the oldest rocks in Colorado that you see out your door here. So they're very, very old. They're a lot older than even North America as a continent, which we'll see in subsequent slides. But by Earth standards, they're comparatively young, okay? And so why do I have a picture of Alaska up here? Well, it turns out that 1,750 million years ago, Colorado looked an awful lot like today's Aleutian Islands do. So I'm going to be trying to use some modern analogs to give you a sense. It's hard for people to imagine, we think about something, oh gosh, that's 100 years ago. That's a really long time ago. 1,000 years. Gosh, I can't even hardly conceive of that. Geologists have to be wrestling with billions of years. And so in that time, the Earth's surface can totally change. And so it's really natural to be thinking about Estes Park the way you have experienced it. But the Estes Park of 1,750 million years ago was radically different. And so we'll try and relate it to other places on the Earth today that it used to look like. Okay, so this is Mount Augustine. It's one of the volcanoes in the Aleutian chain. And basically, the Aleutians is a chain of volcanic islands, and those volcanoes are producing what we call continental crust. So there's two kinds of crust on the Earth. There's oceanic crust, which, as you might imagine, is what floors most of the ocean basins. And then continental crust, which, as the name implies, is what makes up the continents. But you make new continental crust at these volcanic chains. And so when Estes Park was in this chain of islands 1,750 million years ago, that was the newly minted crust that would become Colorado. So the deeper in the Earth you go, the hotter it gets. And that's really important. So you've heard of plate tectonics. So here is sort of a view of the dozen or so major plates that exist on the Earth. And those plates are made of all of the crust plus the upper part of the next layer below that, which is called the mantle. And the mantle has a different composition than the crust, but the upper portion of the mantle is cool enough that it behaves brittly. Lower down, deeper in the mantle, even though the composition doesn't change, it's hotter, and so it behaves differently. So an analogy would be if you take a Hershey bar and you put it in your refrigerator or your freezer, you'll be able to actually kind of snap it. It'll behave brittly. You take that same Hershey bar, same composition, it hasn't changed composition, but you set it out on a hot July day, and it'll get soft enough that you might be able to even pour it into your mouth, okay? So the idea of plate tectonics is you've got this brittle outer layer, which we call the lithosphere, which consists of the crust and the uppermost portion of the mantle that's cold enough that it behaves brittly, like that Hershey bar that you put in the freezer. Below that, the rest of the mantle, even though it's solid, but it flows slowly, okay? Much like taffy. Taffy is a solid, and yet it can flow, or silly putty is another example, okay? And so what you get is these convection cells where that mantle, where it's hotter, it's going to be less dense, and it's going to rise towards the surface, and then as it gets towards the surface, it's going to cool. And when it gets cool enough, it's going to sink back down to the interior, and round she goes. And so you get these big convection cells The lithosphere that's sitting on top of that it doesn't flow in that same way. It's brittle because it's colder, and so it gets broken into these plates, and the plates will move relative to each other, wafted along on these convection cells. All right, and so we live on a spherical Earth. You break that into about 12 of these tectonic plates, and those plates can do one of three things relative to each other. They can crash into one another, they can pull apart from one another, or they can sort of slide horizontally past one another. Okay? Now, the other thing to know is those continental and oceanic crusts that we introduced before. Those behave differently. The oceanic crust is more dense, and so where they crash together, it's going to slide hundreds of miles down into the interior of the Earth where it gets recycled. And that's a process that geologists use. We've got to use fancy technical terms. And so the jargon for that is a subduction zone. And that's what Estes Park was in 1,750 million years ago that fueled those volcanoes. If you've got two plates that are coming together, and they're both continental crust, the continental crust is much less dense, and so those continental plates, they don't want to sink down and subduct, so instead we have what's called collision, and you'll ride one plate piggybacking up on top of another and build huge non-volcanic mountain ranges like the Himalayas are a classic example today. Where the plates pull apart from one another, you get a mid-ocean ridge. So that's like the Mid-Atlantic Ridge, which is a chain of underwater volcanoes that, as the name implies, is halfway between Boston and London in the middle of the Atlantic. And that's where you grow new oceanic crust there. Okay, so that's a little bit about how plate tectonics works. So 1,750 million years ago, Colorado was at one of these subduction zones, like the Aleutians, or this is a picture from Indonesia, another chain of volcanic islands. Every one of those is an active volcano there that is making this new continental crust. So I was saying that this is so long ago that the concept of North America doesn't actually make sense. So let me elaborate on that a little bit. In this diagram, and these diagrams, by the way, are from a book. If anybody's interested in learning more about this, my wife and I wrote a book called Geology Underfoot along Colorado's Front Range, and I've got some copies that I could show you if you're interested, but these diagrams are from that. And in these diagrams, everything that's gray is oceanic crust. If it's brown, that's continental crust. And then if it's black, it's oceanic crust. And oceanic crust is thinner than continental crust, so that's why this black line looks thinner than the continental crust. And so what was the embryonic North America was much, much smaller than what we have today. And the edge of North America was basically where the Wyoming-Colorado border is today. Okay? So Wyoming was part of North America. Colorado was just nondescript seafloor, all right? And attached to that continental crust of the plate that Wyoming was on was oceanic crust. And this is common, like the North American plate, think about it, the North American plate goes from California, the San Andreas Fault, to that mid-Atlantic ridge halfway between North America and Europe. And so the western half of it is continental crust, but the eastern half is veneered by oceanic crust. So it's really common for a plate to be half one and half the other kind of crust, and this plate was that way. That oceanic portion of the plate was converging with another plate. And so just to give you a sense, let me make this arm the plate that had Wyoming on it, or embryonic North America. And where I've got my shirt sleeve, that's continental crust, or continental lithosphere. And then the bare arm part is the oceanic stuff. And it was converging with another oceanic plate here, okay? So bare arm there. And right where my hands come together, that is the plate boundary. And so they're converging. This is oceanic crust or oceanic lithosphere, so it's going to sink hundreds of miles into the interior in a subduction zone. When it does that, the kind of red stuff here, that's magma that is generated as this plate encounters the hot subsurface and starts to melt. That melted material, the magma, is less dense than the surroundings, so it rises just like a helium balloon would rise in the atmosphere, which is more dense than the balloon itself, erupting as a chain of volcanoes. So there you go, or your chain of volcanoes. That's newly minted continental crust. So that is Colorado for the first time, but it's this chain of these volcanic islands. And they're sitting in the middle of the ocean. So if we were to get in our time machine and come back to this room 1,750 million years ago, north is sort of that way, okay? And so if we were to, I'd make sure that I've got a boat. So we've got a rubber dinghy that we're bobbing around in the rubber dinghy. And off to the northeast, over that way, we would have a big volcanic mountain like this. We look to the southwest, we'd see another one rising up. If we looked off to the southeast, nothing but water, okay? But if we look towards the northwest, we'd really have to squint hard, but we might see some waves crashing on the beach. That's the beach of Wyoming, okay? Because Wyoming, as you've got this plate, these plates converging, you're consuming the oceanic material. So there's the edge of Wyoming. It's getting closer and closer and closer and closer. Make sense? Okay, so now let's fast forward. We're able to race up to about 1,700 million years ago, 50 million years later, okay? And 50 million years later, so this is this chain of volcanic islands like I've described. So 50 million years later, at 1,700 million years ago, Colorado crashes into Wyoming. So now everything's the same as what I just described. But as we look over this way towards the Stanley Hotel, it's like the waves are crashing on the beach right here in Estes Park, okay? And that's because Wyoming has gotten towards us. Now, I said that these volcanic islands are actually making new continental crust. So this chain of islands is continental crust. So as soon as the trench, the oceanic trench is the plate boundary. So as soon as Wyoming enters that trench, the plates are trying to drag that down into the interior of the earth, but it's too light and buoyant. It won't go. It's like if you were a mischievous child, which you probably weren't, if you ever tried to flush a ping pong ball down the toilet, it's really hard to do because it's not dense enough. So think about trying to subduct a continent like Wyoming as trying to flush a ping pong ball down the toilet. It's not going to do it. And so instead, you evolve from this subduction zone that I was talking about into a collision zone where the volcanoes shut off and you have faults that stack one slab of crust up on top of another one to form a big coastal mountain range. So this is what Colorado looked like 1,700 million years ago, as this arc was appended onto North America, where Colorado has been ever since. And it was a big coastal mountain range. So, Mount Ypsilon, I'm sure a lot of you recognize this. Mount Ypsilon has this dark light layering, and there it is in close-up. This is the rock called gneiss that I was mentioning is the other really common rock in the Estes Park area. And this is a metamorphic rock. So this is layers of sand and mud, sand and mud, sand and mud that got buried deeper and deeper and deeper over all that time that those volcanoes were active. And then when the plates collided, the heat and the pressure, the squeezing, metamorphosed those rocks and turned them into gneiss. And that is one of the calling cards. This banded appearance is something that geologists call foliation. and foliation is a calling card of these convergent plate boundaries, like the subduction zone evolving into the collision zone that I was mentioning. Okay, so another figure from the book where we're trying to relate what was going on so long ago to something that you could see in the modern world. So this is Australia, and again, the color scheme is the same. Anything that's gray is oceanic crust. Anything that's brown is continental crust. And the continental crust is not just restricted to the continents. If you go to the edge of California and you walk into the waves, you haven't stepped off of continental crust into oceanic crust. It's still continental crust because the ocean's sea levels are always fluctuating. They're sometimes going up, sometimes going down. And so when they're going up, the lowest parts of continental crust are inundated. And so the lighter sort of orangish color, that's the continents that we would recognize today. But the continental crust is actually more extensive than that. So here, the island of New Guinea is actually part of Australia that just had a low spot in between that today happens to be exposed. But 20,000 years ago, when the glaciers were at their peak, they got their water from the oceans. So when you have peaks of glaciers, sea level drops. And 20,000 years ago, New Guinea and Australia were connected. Okay? So Australia is moving north, and as it is converging with the Eurasian plate in Indonesia and then the Pacific plate here in the Solomon Islands in New Guinea. And that's subduction zone. So that's why you have all those volcanoes that we were talking about before in Indonesia. But in New Guinea, right here, and also on the island of Timor here, the Australian continental material has entered that subduction zone, and it's evolved into collision, a continent-continent collision like what I just described. I actually did my PhD on this collision right here. So it's sort of near and dear to me. And that's this is a mountain range here, a coastal mountain range that's basically as tall as the Rockies, but rising right out of the ocean. So that is an analogy to what Colorado looked like 1,700 million years ago, when there was the edge of North America, this thing called the Cheyenne Line, which is really close to the Colorado-Wyoming border. And then those were the newly minted continental crust of the volcanic islands that would become Colorado. Okay, at this time, let me just take a little bit of a digression into what's called the supercontinent cycles. Has everybody heard of the supercontinent Pangaea? A bunch of people have heard of that. So this is what the continents look like. There's North America, South America, Eurasia, Africa, etc. in Pangaea. One thing that people aren't oftentimes as familiar with is that Pangaea was not a one-off. It just happens to have been the most recent supercontinent. So again, if you think about it, we've got oceanic crust that is dense enough to sink and continental crust that isn't. We live on a spherical Earth with these plates. So basically, if we've got one continent over here and another continent over here and it's subducting, you're eventually going to weld those continents together. That's exactly what's happening today at the Himalayas, where India, which was its own continent, has been welded onto Eurasia. Okay? And so if you just run that movie forward on a spherical Earth, the inevitable consequence of that is that all the continents are going to agglomerate together into a supercontinent. Now, it turns out that once you do that, that builds up a tremendous amount of heat underneath, and that reorganizes those convection cells, and so supercontinents inevitably will break up as well. So what you get is this dance of the supercontinents where they assemble, break up, and reassemble the next one on the other side of the globe. So it turns out that this was all happening during the assembly of a predecessor supercontinent to Pangaea known as Nuna. And it was actually two supercontinents in this cycle in the past. So I'm going to walk us through the history of Estes Park, and we're going to see Nuna break up, and then we're going to see the next supercontinent called Rodinia assemble, break up, Pangaea assemble, and break up. And the events that shaped Estes Park and the surroundings basically ultimately owe themselves to this dance of the supercontinents. Okay, so a series of similar collisions to the ones that I just described continued to add material onto the margin of Nuna. So this Wyoming province here, that was the original North America. Colorado got added in this slice called Yavapai. It's named for Yavapai County in Arizona, where I taught for 10 years. And the rocks there are strikingly similar to the rocks here in Estes Park, actually, including some really great climbing on rocks that look similar and are similar ages. Okay, after the Yavapai was welded on, the Matazal was a series of these volcanic arcs that also added in, and the boundary there is around the Royal Gorge, okay, is where you have the boundary between those. So added southern Colorado, New Mexico, and southern Arizona into what would much, much later become what we know as North America. Okay, was there a question?
The red that was over on the left of the slide.
Oh, yeah, so the red here, that's the Mojave, and I don't want to get too far down into the weeds on this. This is a slightly older bit of crustal terrain, but it's largely associated with the Yavapai. So for our purposes, think about it as kind of this light green. Okay, so now the granites that were forming those magma chambers of that first set of volcanic islands, there's not much of that here in Estes Park, but not far away there is a lot of it. So if you drive up Boulder Canyon to Nederland, you're seeing all the granites there are that granite. Turns out, though, that almost all the granite that you see here, including Long's Peak, Lumpy Ridge, and anywhere else you've got granite, is actually about 300 million years younger. It was formed 1,400 million years ago. And it turns out, so there's Estes Park sitting in this Yavapai, and it turns out that this is a bit of a geologic puzzle. The 1.7 billion or 1,700 million year old granites, like the one in Boulder Canyon, those are easy to explain as the magma chambers that were feeding those subduction zone volcanoes. But by the time these granites around Estes Park formed, the edge of the continent was down here at the southern edge of the Matazal, and this was down in Texas and southern New Mexico. And so we're not exactly sure why there was a tremendous amount of volcanic activity here, or magmatic activity. But here, this is the Colorado Geological Survey. You can go to their website, and there's all kinds of really nice examples of Colorado geology here, including all the granites. And it turns out we've got three main suites of granites. The 1.7 billion year old ones I was talking about before, so there's the Boulder Creek granodiorite. And then the 1.4 billion year old ones, there's Estes Park in this big swath of yellow. And you can see that there are a whole bunch of them all through the state, in the San Juans, down in the Sangre de Cristos, the Wet Mountains. They're all over. And not only are they found in Colorado, but you've also got them in Sweden and Finland. And so we were almost surely connected to those areas at that time. And they're a bit of a geologic puzzle as to why they're here. There are ideas, but we don't know for sure. Another thing that is the Iron Dike, and this there's actually a number of these dikes that are dark rocks. Granites are light in color. These are dark rocks called gabbros, and they look like granites except they're dark. That means they have more minerals that are rich in iron and magnesium, which makes them darker in color. And there's a bunch of these along Colorado's Front Range, and the Iron Dike is the biggest and most famous of them. You can see this here if you drive up 34 to Hidden Valley, where the old ski area is, which is now a sledding hill. Just before you get to the sledding hill, if you look off to your right, that's where this photo is taken. And this is actually one of a whole series of these dikes that geologically resemble mid-ocean ridge rocks, and they form when you break up supercontinents. So this is a calling card of the breakup of that Nunes supercontinent that we were talking about. Okay? All right. By 1100 million years ago, like I said, as soon as you break up a supercontinent, you start the first act of assembling the next one. So by about 1100 million years ago, we had assembled the next supercontinent, which is called Rodinia. And there are no rocks in this part of Colorado that are from that time, but the third of these granitic ones, this green body here, is from that time, and that's the Pikes Peak granite. The Pikes Peak granite, as you can see, it's not just making Pikes Peak, but if any of you love going fishing in the South Platte area, southwest of Denver, that's all Pikes Peak granite there as well. So looks very similar in some ways to the rock you've got here, but it's a younger granite, and it has some, it weathers differently, so the topography looks a little bit different. Okay, so unlike the yellow and the pink ones, where there's lots of different bodies here, there's only one of these, and this is the evidence in Colorado for the assembly of the Rodinian supercontinent. Well, Rodinia, in its turn, started to break apart, and when Rodinia existed, this is before there's a North America. What's now North America was called Laurentia, and welded to it, remember this is a global supercontinent, so we have to have some other continental fragments attached to us. So what was attached to us to our west was Antarctica and Australia. So back then, you could have walked from Estes Park to Sydney, Australia, and not gotten your feet wet. Okay? But then those convection cells started to reorganize. You broke that supercontinent apart, and the edge of what's now North America is where it broke apart, and you opened up a brand new, never before seen ocean basin that we know today as the Pacific. This was the birth of the Pacific Ocean as Australia and Antarctica moved off west into the sunset. And so there's only scant and somewhat cryptic rock evidence of this event in Colorado. These red bits here there's the Pikes Peak granite, there's Colorado Springs and Woodland Park right there. So this is Highway 24 going up between those. And there's a major fault there called the Ute Pass Fault. And along the Ute Pass Fault are these really weird rocks that normally you have magma injecting into other rocks, like a magma could inject into a sandstone. But here you actually get sandstone that injects into igneous rocks like granite. It's really quite weird, and there's only a handful of places on Earth where this is happening. We don't have any of it right here in Estes Park, but we do have some not very far away. Most of the best exposures are down by Colorado Springs, but you can even see this closer in places like near Arapahoe Pass. And it's a whole fascinating story, but I always am in danger of digressing and going over time, so I'm going to skip that right now. The next thing, which does have markers here in Estes Park, or it did, is that a line of diamond pipes runs from Boulder up to the Wyoming border. And one of these diamond pipes, although they're called diatremes, and they can have diamonds in them, that's why they're called diamond pipes, but they don't always have diamonds. And the Estes Park one doesn't have diamonds, nor does the Boulder one, But up here, there are several of them on the Wyoming-Colorado border, and those do have diamonds. And it turns out that Colorado was the first place in North America to have a commercial diamond mining industry, where they were mining over there. These things are really fascinating. They're volcanoes that are supercharged with gases. So very similar to like if you take a carbonated soda that's sealed up and you shake it up, and then you crack open the can, you're going to get a big soda geyser. These things are like that. And most processes are happening, most geologic processes are happening on slow timescales to a human. But these things would have been fast even to a human. They were traveling up from deep in the Earth's interior, which is where diamonds form, and that's why they have diamonds in them. And they would come up from about 100 miles below the surface in an hour or so, okay? And they're really quite small. So I've not actually seen the one in Estes Park, but it was supposed to be not much bigger than this room, and it's now been paved over with a parking lot. So, so you can't see it now, but there is one here. And because they come from the Earth's deep interior, they're really dark rocks. So this is one from the Chicken Park diatreme, which is up here near the state line, and you can see that's dark compared to this is one of the 1,400 million-year-old granites. This isn't the one here in Estes Park, but it's similar. So you can see that color contrast. Okay, so they're violent eruptions charged by these gases, actually mostly carbon dioxide gas, just like your soda. And these eruptions were happening about 600 million years ago, and then there was another whole raft of them about 400 million years ago. Okay, so the rocks that narrate the next few chapters of the history have been eroded from Estes Park. They used to be here, but they're not here anymore. And so I'll go through this reasonably quickly, and then the last few chapters we're going to come back to local rocks to see them. But you just go down US 34, US 36, and once you get out onto the plains, you see all these sedimentary layered rocks. And those used to be covering Estes Park as well, but they've since been eroded for reasons that we'll talk about. So even though we don't have them to study here, we do have them nearby, and so we can reconstruct the story. All right? So as that supercontinent Rodinia split apart, the sea began to rise. And the reason is that when you split apart the sea, you get those mid-ocean ridges that we talked about before, and those ridges take up space in the bottom of the ocean. So my analogy for this is you get done with this talk and you're like, man, that was the most boring talk I've ever been to. I need a bath to really enjoy myself. And so you fill up your bathtub to the brim because you're like, it was so bad I need to immerse everything except my nose. All right? When you do that, you're not going to be able to enjoy your bath because as soon as you get into the bathtub, you're going to displace water and it's going to spill out all over your bathroom floor. So the analogy is that we've got a finite amount of water in the ocean basins, and when there's not a lot of those mid-ocean ridges, like the Mid-Atlantic Ridge, the water reaches a certain level. But as soon as you break up the supercontinent and put those ridges in the oceans, there's less total volume in the ocean basins. The water is displaced. It has to go somewhere. The only place for it to go is to flood the continents. Okay? So when you break up a supercontinent, you tend to get sea level rising, and so there's Colorado, and this is a paleogeographic reconstruction that shows that here's the edge of the continent, but this whole western side of it was flooded. And this is one snapshot in time, and it turns out that sea level continued to rise and inundated all of Colorado. Okay? So we don't have those here, but this is Glenwood Canyon. There are granites, very similar to the granites here, in the heart of the canyon, right there. But then above that, you see all these layered rocks, and those are the rocks that were deposited in that sea as it was rising. So for 300 million years, everything was quiet. But about 300 million years ago, tectonics gave Colorado mountains again. I used as an image of this is the Sangre de Cristos. And all these rocks, you can see the layers of these rocks. These are the modern mountains, but all the rocks that make up the Sangre de Cristos, these layered rocks, turns out are the debris left over from an earlier mountain range called the Ancestral Rockies. That is what the event that we're talking about here. And I'll show you some more pictures of those. So this, we've broken up Rodinia. We talked about that with those weird sandstone dikes that are intruding into the Pikes Peak granite. That was 750 million years ago. By 300 million years ago, we were on to the next agglomeration of the supercontinent, and that's our old friend Pangaea. Okay? And so Pangaea assembled as you shrunk the Paleo-Atlantic Ocean, and so the collision happened between the U.S. East Coast and Africa and the Gulf Coast and South America. And that rose mountains, the Appalachians and the Ouachitas, which now are not nearly as big as the Rockies, but back then they were Himalayan in scale. Okay? It turns out that if you were a mountain lover back then, you could have been in Estes Park, and you would have had some mountains, and they probably would have been pretty nice. But if you wanted the really big mountains, go to Amarillo, Texas. Okay? And so these are the Ancestral Rockies, which were kind of the tail end of the big mountains from this continent-continent collision that assembled Pangaea. And so I've tried to superimpose these kind of blue-green areas are the two big mountain ranges that were the Ancestral Rockies. They're called the Ancestral Rockies because they were in approximately the same location as the modern Rockies, but as you can see, not completely. Aspen, Vale, those were all actually underwater because these were island mountains surrounded by sea. And some of Colorado's most colorful rocks were actually made from the debris that was eroded from those mountains. As soon as you raise a mountain range up, processes of weather start attacking it, and you generate sediment, and you transport those downhill. So Colorado Boulder's flatirons are made out of the Fountain Formation, which is the debris shed from those 300-million-year-old mountains. Balanced Rock at Garden of the Gods, the Maroon Bells, and the Sangre de Cristo Mountains, like I was talking about before, to name just a few of the famous ones that are all from that. And they would have looked simultaneously familiar. They would have been in approximately the same location and approximately the same size, but they would have looked utterly foreign. So this is a really cool book called Ancient Denvers by Kirk Johnson and Bob Reynolds, who back then Kirk was the head of the Denver Museum of Natural History. Now he's the head of the Smithsonian. But they commissioned artists to paint pictures of what Denver would have looked like at different points in its history in a geologically realistic way. And so you can see the vegetation was really exotic. The animals, this is a Dimetrodon, a fin-backed reptile. This is so long ago there weren't even dinosaurs. Okay, the dinosaurs hadn't evolved yet. And then this, from my book, is here in red, that's where the debris was laying down that fountain formation. And then the gray, this was the actual island mountain range. And then you can see the shallow tropical sea there. The continents are moving around, and so we were near the equator back then. Okay, we know that those berthed granites, which are the granites around here, those were exposed on the surface. Remember we said miles of material had to have been removed from above them. We know that that material was already removed by 300 million years ago, and the reason this is, it's sort of locally famous amongst geologists as you're driving up Flagstaff Mountain. This is called Contact Corner, and this is weathered granite that's overlain by that, that sandstone of the fountain formation. And the sandstone is laid down on the surface of the earth, so if it's overlaying the granites, you know that the granites were on the surface by that point. Okay. Over the next 240 million years, more sediment accumulated in a now tectonically quiet Colorado. The rock of Garden of the Gods. This is the Pierre Shale, which most of the Denver metro area is built on, including my house. Gives us all kinds of engineering headaches, lots of radon, so a lot of people have to vent the radon from it. This is the Dakota Formation that was deposited on a beach when we were facing an inland sea, and the dinosaur footprints as the dinosaurs were migrating, probably seasonally, down towards New Mexico along that beach. The final sea to cover Colorado retreated about 68 million years ago, and there's our old friend Long's Peak. This is taken from the White Rocks open space on Valmont Road in Boulder. And so these sandstone layers, those are beach sands that have all been solidified into rock. And they were the beaches from that last sea to ever cover Colorado. The reason that that sea drained away was that a new mountain range rose, and that's basically the mountains that we have today. And it was the rise of that mountain range and then the attack by weathering on the material that was being uplifted. That's why all these sedimentary rocks that used to sit above Estes Park are now gone. They were eroded off because you were in the mountains. Boulder, like it is today, was sort of on the edge of the mountains, and so that was kind of where you started to accumulate some of this material. But those earlier rocks, they got tilted up. As the mountains rose, you tilted up the rocks to about 50 degrees in the Flatirons of Boulder, vertical 90 degrees at Garden of the Gods, and slightly less here at like the Devil's Backbone and other areas near Loveland. Yeah?
Do you know what drove that uplift?
Well, that's an interesting question, and that's one of the things that I study. And it basically, there are disagreements about it, but basically it was another one of these subduction zones, like what we talked about before. So there was a plate that is since gone, but called the Farallon Plate, that was sliding underneath North America off the coast of California. And normally that makes mountains only near the boundary. So the Sierra Nevada mountains are the legacy of that. And in fact, all the beautiful granite in Yosemite and Sequoia, Kings Canyon, those are the magma chambers of volcanoes, just like the granites here in Colorado are. But normally you wouldn't affect Colorado. It's too far away. But that plate, the subduction, it can go steeply or it can go shallowly. And it went shallowly. And by being shallow, that caused compression much further east than it normally would be. And we are basically the edge of that. And so there's no more mountains east of us because this was where that plate finally detached. Okay, so the rocks were tilted and buckled. By 37 million years ago, those mountains had been eroded down to an undulating surface with little relief. So this is where Estes Park comes back into the story of what we can see today. So you've all driven up Trail Ridge Road, and I bet you've thought about, wow, this is just a kind of roly-poly landscape here. So there, one of the big cuts, this is due to the glaciers of the last ice age, but it's cutting into this broad, roly-poly landscape. And that's that erosion that was done by about 37 million years ago. At that point, you don't tend to think of Colorado as being a volcanically active place, but we've actually got the biggest volcano known on the surface of the earth. In the San Juan Mountains, it's near Crete, it's called the La Garita Caldera. And those are volcanic mountains and calderas are the most violent of eruptions. And the La Garita Caldera is the biggest of those, and it erupted one of the biggest eruptions known in the history of the world. So the state was engulfed by one of these big volcanic events. This is, again, from that same book, and this is showing a big caldera eruption by Buena Vista that then creates they're called nuear dons. They're ash flows, and they look a lot like a snow avalanche roaring down the edge of, or down the flanks of a mountain, except they're at about 1,200 degrees Fahrenheit. So you're not going to get dug out of that one if you get inundated. And so this, in about an hour, this thing traveled to Castle Rock. And so a lot of the historic buildings in Denver are quarried out of the rock that's left over from that, that's oftentimes called the Castle Rock Rhyolite. But massive volcanoes erupted from here in Rocky Mountain National Park to the San Juan Mountains. The San Juans have the biggest, so there's Wilson Peak, which is an example. But here, this is an aerial view of the Never Summers, and the Never Summers were a bunch of these volcanoes. And basically, the eruptions in the Never Summers blanketed the landscape, and we still see fragments of them today at Spring Mountain and Lava Cliff. Those Laramide Rocky Mountains were buried both by this huge volume of volcanic ash from all those volcanoes, as well as just the debris that was eroded from those Laramide Rocky Mountains. Okay? And so if we look, this 65 million years ago, when those Laramide Rocky Mountains were rising, the landscape, that tilted the layers and made Estes Park high. So the landscape would have looked strikingly like it does today. Okay? But by about 5 million years ago, all those mountains were buried as the Great Plains were filled up by that ash and the debris that was shed off the eroding mountain range and covered up that roly-poly landscape that we talked about. This, from Soapstone Prairie open space, north of Fort Collins, this is showing where those mountains are still buried. So that's why it's a whole lot easier to go up and over the Rockies on I-80 than it is on I-70. And the reason is that I-80, you go west from Cheyenne, and you're like, oh, I'm about to get to the Rockies. And you get up to the Lincoln Monument up on there, it's the Lincoln Highway, and you think, I'm still on the Great Plains, and yet you're on the crest of the Rocky Mountains there. They're still buried. But if we go, there it was 5 million years ago. Down here, so in Wyoming, that's still buried. That's called the gangplank. That's where I-80 climbs over the mountains. But here in Colorado, that cover was eroded. And so what you did is you had buried what was left of those Laramide Rocky Mountains in all this sediment, and over the last 5 million years, you've quarried that sediment out, and you've exhumed those old mountains again. And those are the mountains that we see today. So that re-exposes the Laramide Mountains and all the granites that they contain. And repeated episodes of glaciation during the last 2.7 million years are really what did a lot of that work. And that's why you have, in that roly-poly landscape, really rugged stuff where glaciers were coming down here, glaciers were coming down here. And glaciers are much more efficient at eroding the landscape than rivers are. And so they quarry out a lot of material, and they tend to make really, really rugged landscapes. And the Earth's climate, we're worried about it warming up right now, but over the last 5 million years, it's actually been cooling down. And about 2.7 million years ago, it got to a threshold where it was cool enough for glaciers to grow here in Colorado. Okay, so just to finish a little bit with the climbing, which I know isn't as much of an interest for the folks here, but it'll finish up the story. So some of the famous rock climbing cracks here were formed by this freeze-thaw cycle. You know, you get freezing and thawing. You look at all the granites around here, and you'll see little hairline cracks. And those hairline cracks allow water to seep in. And then when it freezes, the water expands by about 9%. and you'll get a little bit bigger crack. Once you get a crack like that, wind can blow soil in and seeds in, and then you'll get vegetation growing like trees. And the trees, as their roots grow, they wedge these out. And so you get cracks bigger and bigger, and this is on a famous crack on the Twin Owls on Lumpy Ridge that for a climber is hideous because it's too big to stick your hand in like this person is here, and you got to wedge your whole body in. And those can be a real nightmare, but there are some people who thrive on that. But basically, so that geomorphology, that freeze-thaw and the growth of plants and all that, that's geomorphology, which just means the morphology is shape, so it's the study of how the landscape we see is shaped from the rock raw materials through processes of weathering and erosion to produce the spectacular mountain playground that we all enjoy today, and I am done. So thanks for listening. And I'm happy to answer any questions that you have. I had mentioned this book, and so, if you wanted to take a look at it, you can. I suspect it's in the local library. But that has some vignettes about the geology of the things that I was talking about here, including ones of around Estes Park. So, yeah, thanks. Yes?
What are is it still possible for volcanic activity to occur in Colorado?
It is possible, and just I wanted to say too, before I start fielding the questions, I'll stay as long as there are people that have questions, but I know a lot of people have to go, so feel free to leave. You don't need to, you're not going to offend me, so people can sometimes be polite and sit there, but they're like, I really need to go, just go. It's not likely that we're going to have those incredibly violent eruptions. Nobody's worried about that. But there is still volcanic activity, and there are a couple things that sort of clue us in. One is Colorado has an awful lot of hot springs, and those hot springs are indicative of the fact that the mantle underneath Colorado is still hot, okay? And then our youngest volcano is about 4,000 years old, which geologically speaking is young enough. If there's a volcano that's erupted in the last 10,000 years, we consider it possible that there could still be more volcanic activity. And that you can see if you're driving on I-70 westbound by the town of Dotsero. It's called the Dotsero volcano. And if you're driving towards Glenwood Springs, just before you get to the crossing of the Colorado River, look to your right, and tucked up in a little canyon, you'll see the Dotsero volcano. And if you look to your left, you'll actually see what looks almost like black pavement. And that's the lava flow that came down out of that volcano 4,000 years ago. So nothing to worry about, but it's possible that we could have a little bit. It seems to be kind of on its last legs now. Yeah?
At the peak of the Ice Age, how deep was it in Estes Park?
Yeah, well, so the moraines that you see all around, those are telling us as far down the mountain as the glaciers got. And so really Estes itself wasn't covered. It was just to the outskirts of Estes. But in the valleys, those big U-shaped valleys, and all the valleys around here are U-shaped. If you drive down to Boulder or you drive down to Loveland, you're going to be in the Big Thompson or the North St. Vrain valleys, and those have more of a V-shaped profile. And that's because the river can only erode down at its base, and so it just keeps cutting down, 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 and then landslides will sort of steepen the slopes to make a V-shape. Glaciers can roll down and they scour the bottom, but they also scour the sides, and so they'll scour out and widen everything so you'll get those very steep sidewalls and flat valley floors like we see around here. And so basically the glaciers were a couple thousand feet thick in most of those valleys, and you can see where you get a glacier is going to be able to scour deeper if it's thicker. And so where you have a trunk valley coming down and side valleys that had glaciers that were being delivered. Those side glaciers have thinner ice, and so they don't scour as deeply. So what you can do is get a sense of the height by just going up any of these valleys like Fall River Valley or something. And when you see the tributary valleys coming in, you'll see that they're pretty flat on their floor, but where they meet the main valley, there's a real steep drop. Like at the alluvial fan is a good example of that. And that is where you can tell that the trunk glacier went all the way up to where that flat floor of the tributary glacier was, and then up even higher. And then you look on the tributaries, and a lot of times you'll have a steep slope, and then above that it gets flat. There's kind of an inflection point there. That basically is marking about the height of the glaciers. Yeah?
Did the supercontinents, by having all this mass in one spot, did that affect the spin of the Earth? Was it like a wobble? Or?
It's a great question, and it's certainly not something that I'm an expert in, but people definitely have studied that. And the answer is it's a little bit hard to tell, but we do think we have evidence that yes, it would have affected the spin and the wobble of the Earth. There's a thing that goes by the name of true polar wander, where we think that actually almost like you've got the core of a baseball and then you've got the sheath around it. Think of the plates as being like that sheath, and that it could have destabilized things enough that that sheath sort of slipped suddenly. And so in very short order, geologically speaking, continents that would have been, say, at the poles went to the tropics. Yeah. Yeah.
So we have some sea creature fossils at high elevations. We were at the base of the sea at one time.
That's exactly right. And so, the sort of end member of that is Mount Everest. So if you know anything about the climbing escapades on Mount Everest, there's a band that's really difficult to traverse up near the summit called the Yellow Band. And the Yellow Band is limestone, and that limestone is made of all these sea creatures. So the highest mountain on Earth is made of rock that was from the ocean. And so that's typical because of this supercontinent cycle. You'll be an ocean, you'll have sea creatures in it, and then you'll sandwich them together as these plates are colliding, and you'll uplift that rock into the highest mountains on Earth, and there you go. So yeah, we've got a bunch of those here in Colorado. Yeah. Oh.
I know they were just taking new measurements of the mountains
Yes.
in Colorado. What's going on with the mountains? Are they rising? Are they declining?
It's a really, really great question, and it turns out that I sort of skimmed over one thing. I alluded to it a little bit, but the mountains that we have today are not the Laramide Mountains. They're sort of a facsimile of them that has been exhumed. So I talked about that, but it turns out we've got good evidence that the mountains, the Laramide Mountains, while they looked a lot like these mountains, they almost surely were not quite as high as the current mountains. They just, by conservation of mass arguments, you really can't build mountains that high with the kind of that subduction, that flat slab subduction process that I was talking about before. So we know that there was a second uplift event. Geologists do not agree on when that uplift event happened and what triggered it. And so some geologists that you would talk to would be saying that the mountains are tectonically rising today. I don't personally believe that. So there's sort of two camps. And we're still working on that, and there are a bunch of people who, that's what we spend most of our days doing, is doing research on that. There's another caveat to that, and that you might think, well, geez, why is that a difficult thing? You just slap a GPS monument in there, you go and you measure the height, and then you go 10 years later and you measure the height and see if it's going up. It's more complicated than that, and the reason is something called isostasy or Archimedes' principle. And so we all know that from if you've got an ice cube in your glass of water, you know that some of it, or an iceberg, the iceberg that sunk the Titanic, there's the, the old saw of the 90% of the iceberg is underwater, and in fact that's true, and it is about 90% because it's a ratio of the density between liquid water and ice. Remember I said that the mantle of the earth flows. It's solid, but it flows. And so even though this happens on a time scale that we can't observe, but on a geologically rapid time scale, the earth behaves just like an ice cube. And so when you stack those slabs of crust up to build mountain ranges, it turns out that by stacking that slab up, you're causing this mantle to flow out of the way, and so it's going to sink back down. Much like loading a cargo ship with cargo, and the hull's going to sit lower in the water. So that's called a crustal root. When you erode material, then you, let me actually try and go back. I'll keep describing this, but there we go. So this is the image that I was wanting. So let's say you put up a monument on Long's Peak, and you measure it, and you say, yep, Long's Peak's going up. But it turns out that those glaciers scooped out a huge amount of material here in Glacier Gorge right next to it and all the other gorges. So if you put a monument there, your monument is going to be gone because it was eroded away. So when you scoop out that material, that's just like your ship comes into port and the cranes take the cargo containers off, the hull is going to rise up. And so that happens on a broad scale, it's not separate from here and here, it's broad underneath. So actually Long's Peak is rising because in response to scooping out this material here, and that's not a tectonic process. Yes, places like Long's Peak are rising, no question about it. But does that mean that the Rocky Mountains on average are rising? It's not nearly as simple as that. And so what you need to actually do is have some mechanism to measure paleo elevation. And there are some mechanisms for doing that, but they're crude. People disagree about the results. And so there's no real consensus. So some people think that the mountains are rising tectonically today. If they are, they're not doing so on faults. They have to be doing so in a much broader, more diffuse way, like an elevator rising, rather than that stacking that I've talked about before. Other people, like me, actually think that they're not rising, that they might actually be on average going down because you're only going to get about 80% of the rise compared to the amount of material that you scoop out. So if you take a foot off, you're going to get 0.8 of a foot back. And so it's debated. It's a great question, a lot of detail in there that people spend careers on. Yeah.
Is there plate separation going on in the northern Rio Grande Valley?
Another great question. So there isn't what I would call plate separation, but there is extension. So I don't think that we're going to ever, in any time soon, even geologically speaking, see an ocean basin opening where the Rio Grande Rift is. But there is extension. And so one way one way to explain that, and the way that I think does explain it, this is another thing that people disagree on, but most people I think would agree with me on this, and that is, I'll use another analogy. I'm a man of a certain age, and there are other men of this similar age here, and we know that we get a little bit of a spare tire as time goes on, okay? And so if you want to go out and impress your friends on the dance floor, you'll oftentimes sort of suck in your gut and cinch it up with a belt, okay? What you're doing with that belt is you're doing work against gravity. And as soon as you go home and you loosen your belt, gravity takes over again, okay? So that's the human analogy. So what does that have to do with the Earth? Well, when you're crashing these plates together and you're stacking one slab of crust on top of another, you got to do work against gravity. Okay? And so just like the belly, those mountains, as soon as you stack them up, they have gravitational potential energy. The gravity wants to pull them down. As long as you have a belt, okay, the belt can hold your belly in. Well, that's the analogy for the subduction zone, the convergence of the plates. As long as you've got the convergence of the plates, you've got a belt, and you're holding those mountains high. As soon as you shut down that subduction zone, you've loosened the belt. And that happened here about 30 million years ago when that Farallon plate, I told you that it used to exist, but it doesn't exist anymore. It doesn't exist because, let's say this is the North American plate, and this is the Farallon plate, and this hand is the Pacific plate. So you know today the Pacific plate is touching the North American plate, and they're sliding past each other horizontally on the San Andreas Fault. But that's only been the case for the last 35 million years. Okay? Before, we had the Farallon plate. And so the Farallon plate was joined to the Pacific plate at a divergent plate boundary, where you're pulling the plates apart, and the new material is making new oceanic crust. Okay? But as the subduction of the Farallon plate underneath the North American plate was going down, that dragged that plate boundary, that mid-ocean ridge, closer and closer, just like Wyoming got closer and closer to us 1,750 million years ago. So about 30 to 35 million years ago, about at the latitude of LA, that spreading center got to the subduction zone, and that was the end of the Farallon plate. Okay? And it turns out that the North American and the Farallon plate are actually moving approximately the same direction, but at different speeds. So that's why we have the strike-slip motion of the San Andreas Fault. An analogy there is if you've ever been on a train platform in Europe, say, waiting at the station, and there's a train next to you, and then all of a sudden you're like, am I moving or are they moving? Because you'll see them moving. You can be at the same direction but moving at different rates, and it'll look like you're displacing opposite to each other, even though you're not. Okay.
So whatever's going on in the Rio Grande Valley is not plate tectonic.
Well, it's sort of it's an after effect of plate tectonics. So basically, when you shut that subduction off, the high area, now all of a sudden you've loosened the belt, and gravity can win. And gravity is winning. That's what makes the basin and range in Nevada. And the Rio Grande Rift seems to be associated with that, but it's just a little bit further inland. And so it's a small amount of extension, but boy, it makes a huge difference for us because that's why you get that spectacular wall of mountains that is the Sawatch. It's on a normal fault there, and normal faults are where you're dropping down the upper Arkansas Valley, and then further south the San Luis Valley with the Sangre de Cristos as that is spreading apart. But it's not going to make a new ocean basin. Yeah?
So as you think about all this, does climate change have anything at all to do with any of this?
It can, absolutely. So another, not surprisingly, this is an astute audience, so we're getting some good questions. This is going on at a very much more sedate pace than climate change. But climate change, and we're worried today, and I'm very worried about human effects, and not everybody may be worried about that, but most scientists are. But human effects on climate change aren't the only way you have climate change. Throughout Earth's history, there's been climate change, always. The climate is always changing. And when it does, it's going to affect the way the things are ornamented, that geomorphology. So at one level, you might think, oh, this process is too big. Climate change can't affect that. But we think that's not the case. One of the things, so I mentioned that the climate has been cooling for the last 5 million years, okay? And in fact, the climate has been cooling for much longer than that. It's been cooling for about 55 million years. It's been cooling. This isn't 100% accepted by everybody, but it's largely accepted. There's a number of ways to affect the climate that are fed back in by the plate tectonics. So it turns out that about 55 million years ago, you started to get a lot of big mountain ranges. It turns out that's when the Himalayas were formed. Big portions of the Andes were formed then. That's when you got not only the Rockies, but the Sierra Nevada and lots of other big mountain ranges in the American West and others besides. And when you raise those mountains up, we've already said, weather starts to attack them. It turns out that there's two kinds of weathering. There's physical weathering, like the abrasion of a glacier coming down, but there's also chemical weathering. Water is the universal solvent, and it is going to attack every rock and mineral known. Some faster, some not so fast, but it attacks them all. I mentioned that most rocks are made of these silicate minerals, which are called the rock-forming minerals. You take any silicate mineral and you chemically combine it with water, and it turns out that that breaks it down and converts that rock-forming mineral into clay, mud, basically. And a byproduct of that is actually that if you write out the chemical equation that happens, that consumes carbon dioxide. Where do you get the carbon dioxide? From the atmosphere. So if you actually build lots of big mountain ranges on the Earth that you didn't have before, you're going to suck more carbon dioxide out of the atmosphere, and that's going to affect the climate. And so we think that actually the growth of the Himalayas and the Rockies and these other mountain ranges actually is probably the lion's share of why the globe has been cooling for the last 55 million years. That then culminates in the last 2.5 million years with huge ice sheets all over the northern hemisphere, which accelerates the weathering process, and so you draw CO2 out of the atmosphere even faster. Now, what we tend to think of as climate change, then that's on a much larger scale. Then the Earth is orbiting around in the solar system in ways that is being tugged by the gravitational pull of the other planets. Have you heard of the Milankovitch cycles? So the Milankovitch cycles are those. So basically it's mostly the tug of the sun and Jupiter. And there are three main Milankovitch cycles. One is our orbit around the sun, and it's not circular, it's oval. And it only changes its ellipticity by a tiny fraction, 1% or something. But that's enough to affect how much energy we get from the sun. We also have a tilt of the Earth, and that tilt actually changes on a cycle of, if I remember, the tilt is 21,000 year cycle. And so that changes, and that affects how much solar energy we get. And then there's the wobble. We're spinning, and just like if you take a top and you spin it and you give it a lot of momentum, it's going to spin good for a while. And as it loses momentum, it's going to start to wobble. That's called precession. The Earth is wobbling on its orbit, and that affects how much energy we get from the sun. And you add those cycles, those go cyclically because they're due to the gravitational tug, mostly of Jupiter and the sun. And those then cause us to get peaks of more solar radiation, less, more, less, in a cyclic way. And for the last 700,000 years, that's been at a beat of about 100,000 years. So over a 100,000 year cycle, you cool the planet down. As you cool the planet down, you grow big glaciers. Sea level drops because the water that fuels those glaciers is from the ocean. And then at the end of that cycle, you start warming the planet up as those Milankovitch cycles change. and you melt the glaciers. The more you melt the glaciers, the more you, glaciers are really light colored. They have what we call a high albedo. So they reflect a lot of the energy that's coming in from the sun back out to space. So they keep the planet cool. As soon as you start melting the glaciers, you have darker colored rock in place of the glacier, which means we retain more of that energy from the sun, and you start heating up even faster. So you go in a feedback cycle and come out of the glaciers really, really quick. And so we think that, well, we've got excellent evidence that the peak of the glaciation was about 20,000 years ago. And by 13,000 years ago, most of the glaciers in Colorado were gone. Then we got into kind of a sweet spot about 10,000 years ago where the climate is changing a little bit, but not a lot. If the natural cycles were let to run their course, about 1,000 to 2,000 years, we should have started cooling down again. But we're not. And so that's one of the things, these natural cycles are one of the reasons why some people say, well, there's no global warming caused by humans. It's natural cycles. And absolutely true, it's natural cycles. But it turns out that if you actually follow the natural cycles, we should be cooling down, not warming up. So I find that actually even more frightening than if it was just going to be stable. So long answer, but it's kind of a little crash course on climate change at a number of time scales. And at the largest time scales, yes, those have feedback effects. The plate tectonics can affect the climate, but then as the climate changes, that, for reasons that I won't get into now, but can actually, we think, maybe affect the tectonic cycle. So it's all a big, you know, everything's connected. Yeah.
One more question for the official meeting, and then we'll kind of go into
Sure.
after meeting.
Yeah, yeah.
So, go ahead.
Oh,
Yeah.
we need to be the last one.
No,
I
good.
was just curious about the effects of taking all of the substances out of the ground that we've been doing for years and years now. And then they were saying on NPR the other day, looking at the old oil wells and gas wells and thinking about thermal, using those for thermal heating.
Sure. Well, so I am no expert on geothermal heating, so I don't want to comment a lot on that, but those oil wells are a great idea for that. And one of the ways that you can use those is, you know, geothermal energy, you think about places like Yellowstone where you've got hot waters and everything. But as long as you've got hot ground, you could actually take that water and pump it down and heat it up, and that is a heat exchanger, and so you can load that water up with heat and then bring it where you need it to go. Because Colorado has so much heat in the ground, as we talked about before, and is manifest by the hot springs, we've got some real geothermal potential here. And to do that, you basically need to drill a hole in the ground, and if you've got a bunch of oil wells that are already drilled, that makes it much more cost effective. So, so that's at the limit of my understanding there, so I won't say anything more about that. I'm also not an expert in sort of the energy balance in terms of pulling all the coal and the oil and everything out of the ground, but from a systems perspective, which is what I've tried to do here is present you the Earth as an interconnected system. And so I will speak to it, to your first point, on that level. They're not called fossil fuels for nothing. They are fossil fuels because they are fossil. So, you know, it turns out that I use this analogy with my students a lot. If I had a heart attack here and you just left me, and you know, you came back a month from now, I wouldn't be looking so good, right? And the reason would be that bacteria would be attacking the soft tissues. So fossil fuels that we have, those are the soft tissues. When I was a kid, Sinclair's tagline was put a dinosaur, or there was Exxon or Esso then was put a tiger in your tank, and Sinclair is the dinosaur. There are no tigers and very few dinosaurs that we put into our gas tanks. It's mostly plankton. okay? But the plankton have soft tissues. And if you have plankton that are dying, they're sinking down to the sea floor. And there's lots and lots of bacteria down there that break those down. The biosphere gives up organic matter very jealously. It wants to recycle that into the next generation of organisms. But if you have anoxic conditions, although most of those bacteria are aerobic bacteria, they need oxygen to survive. And there are places where you have low oxygen content on the seafloor. Swamps are another place where that happens. If you've ever waded through the swamp muds, it stinks, right? That's hydrogen sulfide gas. Normally, if there's plenty of oxygen, the hydrogen is going to combine with oxygen and make water. But without that, sulfur is right below oxygen on the periodic table, which tells you that it behaves chemically similarly, and you get hydrogen sulfide. So that tells you that you have oxygen-poor conditions. When there's oxygen-poor conditions, you don't have enough oxygen to break down the organic matter, and you make a fossil fuel. Oil or coal or natural gas. So they're fossil fuels. When you do that, if you take a lot of those and lock them up, then there's less carbon to make carbon dioxide. And so the temperature goes down. When you put them back into the atmosphere, voila, you get carbon dioxide. So it takes millions to tens of millions of years to take the transfer, that organic carbon, through this anoxic process and bury them as coal or oil. Millions, tens of millions of years. We're bringing those up, combusting them, making CO2 on the order of hundreds of years. So you just take that balance. There's still organic matter being buried, but it's being buried at a much, much slower rate than we're putting it back in. So from a fundamental systems perspective, it is unambiguous what we are doing. Absolutely unambiguous.
Dr. Abbott, I want
Yeah.
to thank you again.
Yeah. Thanks.
He said he'll be around for
Yeah.
more questions after the meeting, but I just thought we should wrap up
Yeah,
the
absolutely.
official meeting.
Yeah.
Thank you all for coming.
Yeah, thanks for coming. Hopefully